So here's a new definition. Events A and B are mutually exclusive or disjoint if they cannot occur at the same time. So just, to think about that definition for a minute, determine whether the following pairs of events are mutually exclusive. So event A, a movie is rated 4 stars. Event B, a movie is a horror movie. Are those mutually exclusive events or not? And secondly, event A, we randomly select an individual who's a teenager. Event B, we randomly select a senior citizen. Are those mutually exclusive events or not? So can these events happen in one trial or in one occurrence at the same time, or can't they? All right. So are the first pair of events mutually exclusive? No, because they can happen at the same time. No, because they can happen at the same time. In other words, we can select a single movie that is both rated 4 stars and is a horror movie. The second one, are these mutually exclusive? Yes, they are mutually exclusive. We can't, in one single person, have that single person both be a teenager and a senior citizen. So yes, one individual can't be both a teen and senior citizen. So that's the definition of mutually exclusive, and just applied to a couple examples. All right, let's look at some more examples together. So let's say that we roll one 6-sided die. Which of the following events are mutually exclusive events? So if A is the event that the die lands on a number less than 3, B is the event the die lands on an even number, and C lands on a die that, C is that the die lands on a 1. Then are A and B mutually exclusive events? Are A and C mutually exclusive events? Are B and C mutually exclusive events? So first answer those, and then find the probability of each of these sets of events. So find the probability of A or B, find the probability of A or C, and find the probability of B or C. So pause and try these out, and we'll talk about them all together in a moment. Okay, so we roll one 6-sided die. Are A and B mutually exclusive events? So A lands on a number less than 3, B lands on an even number. Well, no, these are not mutually exclusive because, for example, if the die lands on 2, 2 is included in both event A and B. So because there's some overlap, those are not mutually exclusive events. Are A and C mutually exclusive? So A lands on a number less than 3, C lands on a 1. No, 1 is included in both A and B. So again, those are not mutually exclusive events. And lastly, are B and C mutually exclusive events? Yes, these actually are mutually exclusive. Die lands on a 1, die lands on an even number. Those cannot occur in a single die roll at the same time. So since 1 is not even, these cannot occur at the same time. All right, now let's look at finding these probabilities. So we're just going to use the addition rule. This isn't the only way to do it. You could also approach these intuitively. But we are going to use the addition rule to start off. So probability of A or B we know is equal to probability of A plus probability of B minus the probability of A and B. So that would be equal to the probability of A, that the die lands on a number less than 3. Well, it could land on a 1 or a 2, so that's 2 possibilities out of 6 sides of the die, plus the probability that the die lands on an even number, a 2, a 4, or a 6, that's 3 out of 6, minus the probability that the die lands on a value that satisfies both A and B, a number that's less than 3 and an even number. 2 is the only such number, so there's one number or one side of the die that satisfies that. So that's 2 out of 6 plus 3 out of 6 minus 1 out of 6. With fractions, we add or subtract the numerators and keep the denominator the same as long as it's the same denominator for all of them. So 2 plus 3 minus 1, 4 out of 6, which we could also write as 2/3 or 0.66 repeating, or we could round it if we wished. So any of those numbers or any of those values would be good solutions to that problem. Okay, so for the probability of A or C, that is equal to probability of A plus probability of C minus probability of both A and C. And so that's equal to probability of A, we already know is 2 out of 6, plus probability of C, that's 1 out of 6. Die lands on a 1, only one way for that to happen, minus the probability of both A and C occurring. Well, if it lands on a 1, that satisfies both A and C. So we get 2 out of 6, or 1/3, or 0.33 repeating as our solution for that probability. Note that here it's the case that C is a subset of A. C is contained in A. So this is also just equal to the probability that A occurs. Lastly, the probability of B or C. So this is just using our rule above, probability of B plus probability of C minus probability of B and C. And so that's equal to the probability that B occurs, lands on an even number, 3 out of 6, plus the probability that C occurs, 1 out of 6, and subtracting off the probability that both B and C occurs. So how many sides of the die are both an even number and also simultaneously a 1? There are no values that meet that criteria. So minus 0 out of 6, and so 4 out of 6, or 2/3 is our solution for that problem as well. Okay, here's another question for you to try. So this is a more general question. So we have this addition rule. Probability of A or B is equal to probability of A plus probability of B minus the probability of both A and B occurring. So if it's the case that A and B are mutually exclusive, find the probability of A and B, the probability that both occur. And if A and B are mutually exclusive, also find the probability of A or B. So is there some way that you can write that more simply than what's above here? All right, so if A and B are mutually exclusive, that means that A and B cannot occur at the same time, cannot occur simultaneously. And because that's the case, that means that A and B that both occur is an impossible event. So that means that the probability that A and B both occur is equal to 0. Now, what about finding probability of A or B if A and B are mutually exclusive? Well, we know that the probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. But if A and B are mutually exclusive, then we found out just above, we just realized that then this probability would be equal to 0. So if A and B are mutually exclusive, then probability of A or B is simply equal to probability of A plus probability of B. And last problem, or last example here, if the only possible events in a procedure are X, Y, and Z, and these events are also mutually exclusive, where the probability of X is 0.3, the probability of Y is 0.6, what is the probability of Z? So think about that for a moment as well, and we'll talk about it in just a second. Okay, so we're looking at the probability of X or Y or Z, and we know that that probability is equal to 1 because those are the only possible events in the procedure. What else do we know? We also know that they're mutually exclusive. So from what we saw above, this is probability equal to the probability of X plus the probability of Y plus the probability of Z. And we can do that because there's no overlap between any of those events. And again, that's equal to 1 as well. And so we know what probability of x is, that's 0.3, plus probability of y, that's 0.6, plus probability of z, that's what we're trying to solve for, is equal to 1. And so to solve for probability of z, we could subtract off 0.3 plus 0.6. So probability of z is equal to 1 minus 0.9. So 1 minus 0.9, and that's 0.1. So we figured out that the probability of z in this case must be 0.1.